anything. Load may be of a resistor or RL load, or it can be anything. But for starting and to understand the purpose very clearly, let us consider it as a R load, and we have nothing in the circuit, only one silicon control rectifier, and we will have a AC source here. We will have a AC source here, and this is the resistor T1. That's all the circuit. And since the circuit is having only one thyristor, you can easily understand that during the first half cycle of the input supply, the thyristor will be in forward biased condition. That too, when we apply the gate pulse in this particular terminal, when we apply the gate pulse here, when we apply the gate pulse with respect to cathode, then the thyristor will be moved to the on state condition, and the conduction takes place. And since it is an R load, exactly at omega t is equal to pi, the current becomes less than the holding current, and the thyristor will be back to the off condition. And during the negative off cycle, the thyristor itself in reverse bias condition, and even if you apply gate pulse, the thyristor cannot be turned on by the working principle of the thyristor, and from omega t is equal to pi to omega t is equal to 2 pi, there won't be any conduction. And the second off cycle, I mean the negative off cycle of the input supply, will not be rectified, and it will not be available in the output terminal across the load R. It will not be available. So that's why we call this as off controlled off wave. Sorry, this is not off control, off wave rectifier or off wave controlled rectifier. Off controlled rectifier is a bit different, so don't get confused with that. This is off wave rectifier or off controlled rectifier. It means that only off wave of the input supply is rectified or controlled, right? So let me draw the waveforms of this particular we have a AC source. See, the AC waveforms may not be so proper since I'm drawing in the digital board. So you make sure that you draw it properly in your notebook, right? So we have the input supply. This is pi, and this is 2 pi. This is your Vs, and this is Vm, right? And next, when you see the output voltage, this is omega t, this x-axis is omega t. And when you see the output voltage, and consider I am triggering it at some alpha equal to 30 degree or something, right? I am triggering at this particular point. I am triggering at this particular point. So up to this point, there is no output voltage. Up to this particular point, there is no output voltage, and from this particular point onwards, directly from this particular point onwards, the output voltage will start to increase, and it will reach the peak by omega t is equal to pi by 2, and it will comes here, right? And this particular point is called alpha, which is your firing angle, right? So even though the thyristor is forward biased from omega t is equal to 0, until you supply the firing pulses at some alpha, the thyristor will not conduct. Once you apply the firing pulses at alpha is equal to 30 or alpha is equal to 45, 60, whatever may be the angle, from that particular point onwards, the thyristor starts to conduct, and it Okay. And it completes its conduction at omega t is equal to pi. And after omega t is equal to pi, the T1 is reverse biased. Here the T1 is T1 is forward biased. During this condition, T1 is reverse biased. So there is no voltage across the load terminal. During this time, there is no voltage across the load terminal. So if you see this, only one half wave is controlled and it is available across the output. Then once again, in the next cycle, again the same things will be repeated, and you will after some particular alpha, until that the same zero voltage will be available. Until that the same zero voltage will be available up to this, and once again at alpha is equal to some value, the at alpha is equal to some value, the voltage starts to appear and it completes its path at omega t is equal to 3 pi. Right. This is what happening with the single phase of control rectifier. The first thing we have to understand is here is we have only one thyristor in the circuit, and we will be able to control only one half cycle based on the direction of the thyristor connected. In case if this thyristor is connected like this in the same circuit, then we will be able to control only the negative half cycle, only this negative half cycle. Then output will be available here, not in the positive half cycle. But anyhow, only one cycle, one half cycle can be controlled. That's why the circuit name is off wave control rectifier or off control rectifier. Single phase off controlled, single phase off wave rectifier. Now we have to we should try to derive the output voltage equations, both the average voltage equation and the RMS voltage equation. Let me do that. So the thing we have to understand is the average should be taken for the whole cycle, right? And it means that it should be from alpha to it should be taken for the period of 2 pi, and the waveform is available only from alpha to pi. So the average output equation VDC can be written as the average should be taken for the whole 2 pi period, and the waveform is available only from alpha to pi, and the equation for the sine wave is Vm sine omega t d of omega t. This is the equation available. So if you manipulate it, it becomes Vm by 2 pi and minus of cos omega t alpha to pi. Then once again, if we manipulate it, we get Vm by 2 pi, then minus cos phi plus cos alpha. So minus cos phi becomes 1. So the equation becomes Vm by 2 pi 1 plus cos alpha. So now if you know the peak value of the sine wave and if you know the alpha value, you can get the average DC output voltage available across the load terminal or across the resistor R. So this is the average DC output voltage, right? Average DC output voltage. So next we have to get the derivation for RMS, right? The same limits, same equations, but the only thing is it should be squared and it should be taken root, since we know the formula RMS, and thing is 1 by 2 pi alpha 2 pi, everything is same, only thing the equation should be squared. Vm square sine square omega t d of omega t, and it should be taken square root 1 by 2. So this becomes Vm square by 2 pi. Then this becomes alpha 2 pi. The sine square omega t, we can write it as 1 minus cos 2 omega t divided by 2. Then d of omega t. Right. So this is the equation. And anyway, there are a few more steps here that you please take care. Then the final answer I'm writing, because I don't want to spend time on the this trigonometry. It becomes Vm by 2, then 1 by pi minus alpha plus sine 2 alpha by 2 whole power 1 by 2. This will be the final equation. Right? If you substitute alpha and pi, you can understand that. So this is the V RMS output RMS voltage. So even though the output voltage is DC, we consider this as a DC because the output voltage is not going to the negative peak negative side. Even though it is considered as an AC, it has both average value and RMS value. Both are different. If it is pure DC, average value and RMS values are same. If it is pure AC, there is some RMS value, but average value is 0. But when you have modified, or if it is not a pure DC, or if it is not a symmetric sinusoidal wave, then we will have a different AC value and a different RMS value. That's why we have both average DC output voltage and as well as RMS output voltage. Both are really different here. That we should understand from this. Then we will move on to the full bridge converter. Next is single phase full bridge rectifier, or we can call it as full converter or full wave rectifier, whatever it may be. So the circuit will be, you know the circuits since you have already completed all laboratories, you know the circuits and everything. The load can be anything. It can be an R load, or it can be or load, R load, whatever it may be. So as of now, I'm considering it as R load, and let us derive the equations. Then we can. This is an ideal case, right? This is an ideal case, and nothing is inductive. Everything is resistive, and there is no source inductance or load inductance, nothing. So this is the case that we are considering here. So let us analyze the working principle here. I think I have already explained these working principles in the class before the laboratory, but once again I'll spend some time on this so that whoever has not listened during the time, they can understand the working principle of the full wave rectifier. Because in laboratory this has been explained to you. Just a minute. சொல்லுங்க சார். ஆமா ஆமாங்க சார். வெங்கடேசன் சார் கேட்டு வெங்கடேசன் சார் கலெக்ட் பண்ணிட்டு உங்களுக்கு தரேன் அப்படின்னு இருக்கிறாரு. அது வந்ததும் உங்களுக்கு நான் 130 பேர் அவங்களுக்கு தந்துடுறேன். ரைட், நான் கொடுக்குறேன்னு சொல்லி இல்ல அவங்க எல்லாரும் கேட்டாங்க கூப்பிடுங்க சார், நானே வந்து கூட எக்ஸ்பிளைன் பண்றேன். ஏன்னா வேற யாரும் பொருள்